All right, recording is rolling. It is Wednesday, December 6th. I have a rotational inertia lab for you guys. We're going to do a 5-part write-up as part of this. Right, here's how it goes. Right, what is the question? The question here is going to be, what is the rotational inertia of this crazy looking pipe system? You guys can see it right here. Earlier today, I filmed a 30-second video of the same motion, right? And here's the cartoon version of it here. Right? So, you guys see this is like free to rotate about its axis. If I grab it in the middle and like rotate back and forth, ooh, I feel some resistance to change in motion. Oh, that's like inertia. It's rotational sense. That's rotational inertia. How much rotational inertia? Can I quantify that? And what would the units be? Or maybe some kilogram meter squared, something like that. Right? That's what we're going to find out empirically. Right? So like this thing can rotate. Right? Let's look at this setup. While you guys, it might be a good idea to jot down this. Right? While you guys are that 5-part write-up. Right? 5-part write-up. Right? You guys got to do this write-up. I have a scoring rubric. I'll score you guys near the end. Well, I'll have you guys score yourselves near the end of class. Right? Right. So here's the setup. We're going to put a lab mass here, attach it to a string, wrap that over a pulley system that's wrapped around the central axis. And then this weight is going to cause a tension in the string at this rate. This provides a torque, R cross F, which is going to cause this to speed up spinning, which is called angular acceleration. You guys remember torque equals R cross F, but torque also equals I times alpha. And there's enough information lying around where you can solve for capital I, which is rotational inertia, as we were going this, right? So the question is, what is the rotational inertia of the system? How many kilogram meters squared, right? List what measuring tools we're going to use. Right. So think about that as we're going along. Data gathering procedure. So you guys remember how that goes? Want to do a brief description of the setup, maybe a couple of sentences. Got some pipe system for you to rotate, lab weight, string. Then what tool did you use to measure what variable? Right, got a whole table down here, about to go over with you guys. Okay. Then analysis. Now analysis, sometimes it's you apply equations to solve for specific things. We're going to do a little bit of that. Sometimes it's a graph or some property of a graph, which is actually how we're going to finish this. We're going to finish this with a property of a graph, right? And then conclusion. Make sure your conclusion answers your question. Or if the question is what's the rotational inertia, the conclusion is rotational inertia equals some number of kilogram meters squared for this particular system. Okay? Right. While I got this textbook puzzles, chapter 8, due Friday. Remember yesterday we took all day to I showed you guys how to set up and think about to solve them. Right? We're looking at the solutions, right? I'll pick this up by Friday. And then on your desk today, you guys see your next quiz, rotational dynamics quiz. Let's have that due after the weekend on Monday. Right? So you guys good with what's going on so far? Okay. Right, there we go. Yeah.
Could you zoom in a bit on the table?
Oh, this table? Yeah, let's do that right now. This table, because I want to modify this table a little bit. Right, so as we're going along, so it won't be exactly this, but it'll be pretty close. So if you're writing on paper, make sure your name is on your paper, right? Or if this is in your lab notebook, that's okay too. So this is rotational inertia lab. Right? Let's make a 10-column table. Can you guys do 10 columns? Right? Conveniently, this paper is a little over 10 inches. I'm going to do something I never do in this class, which is break out the inches. Ooh, all right, rare day. So I'll get 10 columns going. 10 columns, right? 10 columns, right? Just like usual, I want one row for variables and the next row for the units. And then everything after that, I'll record numbers for data, and all the numbers will have the attached units embedded in that second row. Okay. So I'm getting 10 columns going. And then the first 2 rows I'm going to block off for variables and units. Okay. Right, so let's have different trials going on. 1, 2, 3, 4, 5. Right. I need to measure what's the radial size of the central pipe, right, which is not very much. It's a little over a centimeter, but we'll get that measurement. Ooh, maybe with a ruler. What's the radius? Right. Now I'm going to say in meters. I might measure in centimeters, but I want everything to be in base SI units. So small number of meters. I'm going to swap these two columns. Let's say X, what is the falling distance, right? So of this lab mass. You guys see this lab mass can fall some distance. I've labeled X. It's going to label it here. Also in meters, right? I might say H for height, right? Oh. Okay, I need to record what is that lab mass in kilograms. Of course, the box of lab weights, the biggest one is 1 kilogram. So it's going to be some decimal here, right? A lot of these numbers are going to be small, right? Oh, how much time does it take to fall that distance, right? So I'm going to say time measured. Right, here's where I'm going to make a modification from the printed table. I'm going to have 2 columns for time. There's going to be measured time in seconds, right? You guys see the stopwatches on your desk? About to have like 3 volunteers, so we'll do 3 times and then an average, right? And the next column, let's do average time in seconds, right? What I'm trying to get at here is, you guys know one thing that AP always scores on this question. One of your FRQ questions will be experimental design. You have to write a procedure like we're doing today, and one of the points is always do multiple trials and take an average to reduce experimental uncertainty. That's always a point. Right, so that's what we're doing right here. Right? We're going to make believe we run this 3 times, but just to save us a little time, we'll do 3 different stopwatch times and make believe that we did it 3 separate times. Okay, okay. We'll do 3 and take an average. Right? So you guys got stopwatches. You guys are going to tell me how much time. Okay. So that looks like all the measured data, and then I have a few for calculated data points. I meant to explicitly mention, although you guys probably figure out by now, how we usually do labs is I give you guys all the equipment, have you guys go back to the lab area and do everything yourselves, right? This one's going to be like a guided lab. So I've got everything in front of the classroom here, right? And advantage of the guided lab is that I can make for sure, every step of the way you guys know exactly what's going on. You'll have all exactly the correct data. It's all going to be correct, right? So, all right. So that's about all we can measure, right? Now, how about some of these calculated values, right? Like linear acceleration. I think this lab mouse is going to be accelerating down. Like if it starts from rest and it starts moving, right, okay, right there's some kind of acceleration involved, right? It's probably going to be a uniform acceleration. And you know what? If it starts from rest and it falls some distance and some time, hey, that's 3 kinematic values. Ooh, do you guys think we could 3 kinematic values? Once you know how far and how much time and starting from rest, right? I guess that means this one goes away. You can solve for acceleration. For that matter, you could also solve for crash speed. We're not so interested in that, right? But acceleration, we definitely are. Hey, can I take, so this piece is 0, right? So x equals 1/2 at squared. If I'm solving for a, I can take this 2, cross multiply it, 2x, divide down that t squared, 2x over t squared. Is that what acceleration? Now that's the linear acceleration of the lab mass. That'll be an important value to have, right? You guys about to see why. So let's do a column for acceleration in meters per second squared, right? And we're getting that by doing 2 times the falling distance divided by the falling time squared, right? You guys have seen this several times before in this class. I remember one place you saw it was Atwood Lab. You guys did a version of this, calculated the acceleration. Right? You guys remember, here's a side thought. Free fall gravity, let's use 9.8 meters per second squared, right? That's like the maximum value of what this could be, right? I think it'll be a lot closer, but okay. Well, if you know the linear acceleration of this lab mass, that's related to how fast this whole thing is speeding up spinning, because right, it's literally tied to that central axis, right? So as this accelerates falling in a linear sense, this is going to accelerate in a rotational sense. That's called angular acceleration. I'm going to call that alpha. That's going to be in, what's the unit for angular acceleration? Radians per second squared. Yeah, right. And if you know the linear acceleration and you know the radius of that central pipe system, right, then here's that connection right here. You guys are turntable physics, right? There's that connection. So alpha is just A divided by R. That's it, right? This could be the cross section of that central pipe, right? Of course, it's real small. It's just like that little circle right there. So I'm gonna say equals linear acceleration divided by radial size. That's how we're going to calculate that one. So all these first variables we're measuring, right? Then we're doing some calculations here, right? Right now, going in. What is the tension in the string that's causing that angular acceleration? Because anything to do with acceleration, well, there's some kind of force involved, right? Tension string. Now you might think, well, isn't the tension string just equal to the weight? That's almost true, but not exactly true. I think we talked about this yesterday, right? Talked about this yesterday, right? If it was at rest or moving at constant speed, then the tension would be equal to the weight, right? But the fact that it's accelerating down, I'm thinking back to elevator physics. I think we talked about this yesterday, right? Because remember elevator physics, this guy's accelerating downward because there's a net force downward, right? That the tension in the cable is m times g minus a for this, right? This goes back a few months ago. Right? You guys remember that, right? You should be able to derive this, right? We talked about that yesterday too. So we're gonna calculate the tension force, F sub T tension force measured in newtons, right? We're going to calculate that by doing the hanging mass times G minus A, right? And then the last column I want here is for torque. Right? So Greek letter tau, that's going to be in Newton meters, right? And that's equal to R cross F, right? Okay, so that's from the string, right? Here's the radial size of the central pipe times this force in the tension in the string is the force, right? Got an R cross F. You see it's causing a torque. Right, so we filled out that table like in order of the way we're going to collect this information, right? But maybe it makes sense like why we need each one of those columns, thinking backwards, right? Thinking backwards from what are we trying to find? We're trying to find rotational inertia, right? And I can think of that sort of like through a torque formula. I know two formulas for torque. Torque equals R cross F, but torque also equals I times alpha, right? The way we're going to finish this lab, right, think of this whole thing backwards, is we're going to have a graph of torque versus alpha on a set of axes, right? And I bet that's going to line up in a straight line. This equation suggests that it should. This looks a lot like y equals mx, doesn't it? Right? I bet rotational inertia is going to be the slope of a straight line on a torque versus angular acceleration set of axes, right? Right. So we need torque. That's the last column there. Where do we get that? We get that from R cross F. Radius we can measure, force, the tension, well, you need to calculate that from lab mass and acceleration. Angular acceleration you can get from linear acceleration divided by radius. Okay, so that's why we need each one. And this acceleration values we get from kinematic motion. So I'm doing falling distance and falling time starting from rest. Right. So you guys see why we need every single one of those variables to hone in on this right here. And it's all leading to this. Torque equals I times alpha. Okay, like I said. All right, so let's get some rows on here. I'm gonna have 5 trials. We give box silicon cells 1, 2, 3, 4, 5 trials going on. Right. Every one of these cells will have one number in it, with the exception of the measured time. I'm going to get 3 values from you guys. Right. So trial 1, 2, 3, 4, 5, or if you like, 3, 6, 9, 12, 15, something like that. Right. And some of these are going to be controls, like the radial size of this is going to be locked in some value. The falling distance can be locked in some value. So these columns are going to be controls. Let me go and get those. Right. So I'm going to break up the ruler. Ooh, ruler. Think about the measuring tools. You guys know if he makes a big deal about that. Looks like the diameter of that central axis is 2.2 centimeters. Therefore, the radius would be half of that, 1.1 centimeters. But I don't want centimeters, I want meters. I'm going to call it 0.011 meters. Okay? That would be controlled, so that's the same all the way down. Okay. What's the falling distance? X. Oh, I have a meter stick lined up right here. The falling distance is about 70 centimeters. 70 centimeters. Right. Guys, how many meters is that? 0.70. There you go. And that'll be also controlled, so that'll be the same all the way down. Right. Now the lab mass. Now this is going to be sort of an independent variable. I'm going to swap this out right throughout the lab. Right. I found some values that work pretty good. We're going to start with the 200-gram lab mass. Right, guys, 200 grams. How many kilograms is that? 0.20. Exactly. There you go. Right. And then we'll increase that as the lab goes on. Right. Right. So we got to figure out how much time does it take to fall that 70 centimeter distance. Right. We're going to get 3 values and take an average. Right. Right. You guys ready with some stopwatches? You guys ready? All right. Let's see. Who wants to volunteer stopwatch? Who wants to volunteer stopwatch time? Right. How about let's go Alec. How about Sarah? And yeah, how about oh wait, hold on. You guys have the same. You have a separate stopwatch. Steven, Steve. All right. Yeah, go ahead and grab a stopwatch over there. All right. So go, Alex, Sarah, and Steve. Right, stopwatches. Okay. There we go. We're gonna get 3 measured times. This is measured right here. All right, so set this up. Or you guys can do it at your desk. Yeah. All right. All right, so I've got 200 gram lab mass right here. I attach it right there. Right, just all right, got this wound up to the 70 centimeter mark. All right, sit right there. All right, you guys ready? All right, starting to rest and go. So this first one takes a while. And you gotta stop it as soon as it hits the floor. Right, so it is accelerating. Kind of hard to tell, but it is speeding up, spinning. Kind of tell. Right, and stop. Right. Oh, guys, it's still spinning. Right? Why is it still spinning even though it's not being pulled?
Inertia.
It has inertia. Ah, there you go. Right. Now it does eventually slow to a stop because there's a little bit of friction. Right, we'll talk about that later. Right, I'll come back. Right. So, Alec, what'd you get? 28.13 seconds. Sarah, what'd you get? 27.91. Steve, what'd you get?
28.08.
28.08. Right, let's take an average. So open parenthesis, 28.13 plus 27.91 plus 28.08 close parenthesis divided by 3. I'm getting 28.04 seconds. Okay. We're going to make believe that we did that 3 times, but class time to do it properly. Cut a little corner there. Okay. All right, let's do the next one. Next one, I'm going to add on 100 grams. So that'll bring it to 0.30 kilograms. Okay. But have to wind this thing back up. So gotta get that. Rewind. It's rewind time. Yeah, rewind. Rewound. Patch on 100 more grams. All right, guys, ready? Ready? All right, here we go. And go. Ooh. So, like, it might be accelerating a little bit faster than last time. I think you can kind of tell, right? I think it's accelerating faster enough that you can kind of tell. And stop. Seemed a little too fast. I don't know. We'll see on the graph how this lines up. All right, Alec, what'd you get? 20.13. Sorry, what?
15.
Oh, 15? Okay. Sarah, 20.19. Steve,
10.35.
20.35. Okay. All right. Let's add on 100 more grams. Bring it up to 0.4 kilograms. Rewind. What's that? There you go. Rewind. Now I got 400 grams of this thing. All right, guys, ready? Yeah. And go. You can tell just looking at it, it's definitely accelerating faster than before. All right, and stop. All right, Alec, how much time? 16.37? Oh, 47? All right, Sarah. 16.69. Steve.
16.50.
16.50?
15.
Oh, 15? All right. That's 16.47. 16.69. 16.15. 5 by 3. That's 16.44 seconds. Oh, I forgot to average the last. 20.23. Good. All right. Yeah, thanks, dude. Let's throw on 100 more grams. Bring up to half a kilogram. Right, I'll get to the big lab weights. We're about to do. Half a kilogram. Catch that. All right, you guys ready?
Yeah.
And go. Steve.
14.46.
14.06. All right, Sarah. 13.96. Alec. 14 flat. All right. 14, 1396, 1406. All right. And whoops, what's that? Yeah, 14.01 at round 2. Thanks. All right. I'm going to add on 200 grams for this last one. Bring up to that many kilograms. One. All right, so 200 grams on top of the half kilograms right there. All right, I think we're ready to go. All right, you guys ready?
Yeah.
And go. And stop. Alec. 11 point what? 62. All right, Sarah. 1163. Steve.
11.62.
1162. All right, I think it's gonna average to 1162 something. It's gonna kind of round down a little bit, right? Yeah. All right, so we got our times. Right. Oh, remember starting from rest, fell this far in this much time. You can calculate acceleration. So I talked about that before getting to data. It's 2x over t squared, right? And that's something you guys have seen in the past too, right? So 2 times the falling distance divided by average times squared. I'm getting, no, this is a tiny acceleration, but it makes sense that it would be, right? 0.00178 meters per second squared. Right? And all these numbers are in base SI units. So yeah, it's gonna be a tiny number. Right? But that's okay, because I know the maximum free fall, if it was in pure free fall, it'd be 9.8 meters per second squared. Right? It took a long time to fall that distance. So yeah, okay, that looks believable. Right? Right, next one. One reason I really like this model calculator is if you're doing similar type calculations over and over, which we're doing right here, you can just scroll up, scroll over. Anything that's the same, just leave it there, locked in place. And anything that's different, just pop in the new number. Right, it's squared, taken care of. Right, so 0.00342 meters per second squared. Scroll up, scroll over. 1644. That's 0.00518 meter per second squared. Scroll up, scroll over. 14.01. 0.00713 meter per second squared. Scroll up, scroll over. 1162. 0.01037 meter per second squared. Ooh, right there. Right. Remember, if you know the linear acceleration of the falling mass, just simply divide by this radial size, and that will tell you the angular acceleration of the rotating pipe system. Right, so what we do right here. Right. Remember, that's, I'm thinking of this turntable poster right here, right? Right. The cross section is pipes, like a little tiny turntable. Right, so that's where the string is bound around. So 0.00178 meters per second squared divided by this radius of 0.011 meters. That's 0.162 radians per second squared. Okay? scroll up, scroll up. All right, well, okay. We're 342. 0.311 radians per second squared. 0.471 radians per second squared. 713. 0.648 radians per second squared. And 0.943 radians per second squared. Okay, so radians per second per passing second. It was speeding up spinning it. How many radians per second squared? Okay, are we good so far? Okay. Any questions so far? Are you guys good with where these numbers come from? Okay. All right. I'm keeping kind of a fast clip here, but just to keep everything in this class period. All right, what's the tension force? All right, now remember, the tension is probably pretty close to the weight, but slightly less because it is accelerating down. It's not going to be a whole lot less, but just to just good practice to do it correctly, right? Elevator physics, m times g minus a. So take this mass, we had 0.2 kilograms, g minus a. Let's do 9.8 meters per second squared minus 0.00178 meters per second squared. Oh, okay, so I'm thinking even if you forgot to subtract the acceleration, it probably wouldn't change the answer a whole lot, right? I'm going to round to the hundreds place, 1.96 newtons. Right, let's 0.3 kilograms. This is 0.00342. All right, doing 2.94 newtons. Then 0.4 is 518. Got 3.92 newtons. We got 4.90 newtons. And finally, 6.85 newtons of tension. Okay. As a side thought, right, if you had forgotten, oh yeah, go ahead.
Is there a reason why we did? Oh wait, no. Never mind. I forget.
All right.
I was gonna ask why lots of we just jumped like 20, an extra.
Oh yeah.
We jumped it like twice how like the normal step is. So.
Exactly. Okay. Yeah. So you're looking at, I had 100 grams at a time, right? Until last step I had 200 grams. Right. Okay.
0.60 would be of course about like 5.88 about.
Oh, okay, yeah, it's somewhere like halfway between those. If I did like 0.6 kilograms, yeah, it could have something like that too. Right. Right, if you forgot to subtract a and you just did mg, it wouldn't be a whole lot different. So just for curiosity, what's 0.7 times 9.8? Right, that gives you 6.86 newtons instead of 6.85. Okay, so not a whole lot different. Right, and then finish off this table. Torque. Now remember, two perspectives on torque, and we can do the R cross F perspective right here. And then later on, it's going to link to I times alpha, which is going to lead us to the answer. So remember, the question is, what is I, rotational inertia? So this R cross this F, right? R cross F. Why not? Okay. So here's radius, here's force, right? R cross F, right? Now, remember, cross product means you only multiply the perpendicular components. But conveniently, for this type of setup, no matter how you orient the string, as long as you're pulling horizontal, right? You can pull at any angle, and the radius will naturally always set up perpendicular to the tension force, right? The same thing with the turntable. And so I can just very simply multiply these together. I don't have to worry about sine of theta. Sine of 90 degrees. 0.011 radius, that's meters radius, times 1.96 newtons force is 0.022 Newton meter. I'm rounding a little bit there. Right, scroll over. So 2.94 force. 0.032 Newton meters. Of course, the radius is locked in place, so I'm just leaving that there. But the force is changing. 0.043 Newton meters. 0.054 Newton meters. And finally, 0.075 Newton meters of torque. All right. There's the table. Right. Are we good so far? Good so far? We got that? Okay. So there's a whole table. Right, now it's graph time, right? And we're going to do graph inspired by this equation right here, torque equals I times alpha. Because here's different torques, here's different alphas, torque and alpha, right? Now Newton's second law of motion, but the rotational context is torque equals I times alpha, right? I bet if we plot these two on a set of axes, torque versus alpha, they should line up in a straight line, and the slope should represent the answer to the question, rotational inertia. Let's do that right here. Right, guys, maybe make a graph. Make a graph. Yeah. Right. So we're doing torque versus angular acceleration. So make a title: torque versus angular acceleration. Boom. Okay. Torque is measured in Newton meters. Angular acceleration is measured in radians per second squared. Okay. And the names of those characters are tau and alpha. Greek letters, tau and alpha. Okay. Let's, so everybody's got the title, everybody's got a couple of axes, everybody has the axes labeled with variable unit. Everybody has all those things. Okay. Now let's scale these axes. So torque goes as large as 0.075 Newton meters. So I got to scale that accordingly. Oh, bam, bam, bam. All right, let's go 0, 0.025, 0.050, 0.075. Okay. Okay. There's torque scale. Okay. How about alpha, angular acceleration? Well, the largest value is just a little bit less than 1 radian per second squared. So let's go. How about 2, 4, 6, 8, 10? How about that? So 0, 0.2, 0.4, 0.6, 0.8, and 1.0 radian per second squared. I like that. Right. Right, let's plot a bunch of coordinates. Right, remember plotting these two columns against each other. So like x, y, x, y, x, y. Right, alpha tau. Right. So 0.16 radian per second squared, right about there, corresponds to 0.022 Newton meters of torque. Bam! There's the first point on the graph. Right. Next coordinate, 0.31, 0.032, 0.31, 0.032. Sorry about that. Bam! Next coordinate, 0.47, 0.043, 0.47, 0.043, 25, 30, 35, 40. 43 is right about there. It's right there. Bam! Fourth point, 0.65 about, 0.054, 65, 54, 555. Bam! Right. Yeah, ooh, look, these are all lining up a straight line. See that? About one more point. So angular acceleration of 0.94 radians per second squared, right about there. I think. Got 0.075 Newton meters of torque. Bam, right there. Right, there's all 5 points. Look at there's these. They all line up in a straight line. Straight line. It's a linear relationship. So let's do a line of best fit. Okay. And oh, what's this? Guys, does that line go through the origin? It clearly does not. That means something. Guys, what does that mean? The fact that there's an intercept on this line. I'm gonna rewind this while you guys are thinking about that. What does it mean? That intercept right there. Yeah, what do you think? There's a little bit of torque, but there's no angular acceleration. Yeah, what do you think?
Static friction.
Friction! Yeah, static friction. Yeah, frictional torque in this case. We usually measure torque, usually measure friction in like as a force in newtons, but there's such a thing as frictional torque too. You can think of it that way, right? Like, because now I got this thing rewound. What if I put a little tiny 50 grammer on this guy? So it's 50 grams. And wow, oh look, it doesn't move, Right? That's not enough force, not enough tension to overcome the static friction. Yeah, so this is frictional torque right here. Torque, friction. Right? Now, once you go beyond that initial frictional torque, then it still lines up in a straight line. Right? So this is really like torque equals I times alpha plus the frictional torque. Right? Doesn't that look like y equals mx plus b? Right? So we can still get rotational inertia. Right? Now, on the pre-printed table, I had an extra column that we didn't really do class in the table, which was, well, if you just divide torque by alpha, that should be I, right? But that's not exactly true, because that's assuming that it goes through the origin, which isn't quite correct. So we have a better version that we're doing in class. Can I do slope is rise over run, and that's the answer to the lab, right? Rise over run. Right? So this I, rotational inertia, is equal to change in torque over change in angular acceleration. Right? This rise over this run. You know what? It looks like my line pretty well goes through these 2 points. So I'm going to say it does and just play off those. Right? Right, so here's data table. Let's do rise over run. So rise is 0.075 minus 0.022 Newton meters. And the run is 0.943 minus 0.162 radians per second squared. Right? So rise over run. So, right. So I equals 0.075. Oh, I meant to. Okay, I forgot one thing. That's okay. Right, got the answer here. 0.0679 kilogram meter squared. Because I know I is something to do with like mr squared, but some of them are squared. So mass is in kilogram, radius is in meters. Squared. Okay. There you go. That is the rotational inertia of that pipe system. Okay. I forgot to do something before we ever started collecting data. I wanted to get the estimated rotational inertia from a completely different point of view. Right? But before I switch over in that thought process, is everybody okay with this? Where I got this from? How that works out? Okay. That's how you can quantify. Remember what this means. This means if you grab the metal and start shaking back and forth, that feels some resistance to change in motion. Now we can quantify that in the unit kilogram meter squared. Is this many kilogram meter squared? That's the resistance to change in rotational motion. Okay. What I meant to do before we ever started this lab, and I'll do it right now, is this kind of looks like this, doesn't it? Right? And in fact, it's got like a couple of masses on here. You guys see that little masses? Well, maybe that's kind of like a couple of these going on, right? I bet I could get a pretty good estimate of what the rotational inertia would be by adding up all the bits like this, right? Here's what I do. Before school started today, I got what is the mass of each one of these arms, which doesn't exactly want to picture. There's like a T piece in the middle and pop in the arms, right? Each of those is so many grams and so many centimeters long, right? If you add everything up, so I'll do 1/3 ml squared for this arm, 1/3 ml squared for the other arm, then mr squared for each point. Right? So 2 of those. Right? What do I get? I'll just do this on my calculator screen. So what's 1/3 mass of the arm was 0.1397 kilogram times length squared, 0.62 meters squared, right? And then there's 2 of those, right? Plus, we got a couple of bobs on the end, right? That's well, 9.4 grams, but divide by 1,000 to convert to kilograms, times also the same location, 0.62 meters away, and then square that. And okay, there's 2 of those. Did I say 2 already? No, I haven't done that yet. So times 2, because it's 1 half on each end, right? Put it all together, right? I'm gonna get, yeah, right, 0.043 kilogram meter squared. Well, I've been doing the same calculation all day, so I got it written around here. Right? I was going to predict before we started that that would be pretty close to the rotational inertia. Right? Now, notice I left off the central axis, so maybe this is a little bit of an underestimate. Maybe some other reasons too it might be an underestimate. Right? But the answer should be pretty close to that, and that's exactly what we got. I mean, it's the same order of magnitude. It's a little bit bigger. Right? You guys have that? Right? You guys good? Right. Go ahead right now. Let's do this 5-part write-up. 5-part write-up. Right, so go ahead, start doing that. I'm going to give you guys a few minutes to do the 5-part write-up, and then I will pull out the scoring rubric and score yourselves right before the bell rings. Here we go. 5-part write-up. Okay. Here, help you guys out a bit. Question: what is the rotational inertia of the pipe system? Boom, done. Measuring tools. What measuring tools do we use? What did we have to directly measure? Okay. And also the lab weights too, right? Yes. Throwing scale for lab weights, right? Okay. That. Okay. Right. Procedure.
Mass of weights is no.
Yeah, it might be a good idea just for completion to also throw in the scale. Yeah. Right. Procedure. Right. Briefly describe the setup in a couple sentences. Say, okay, use this tool to measure this thing. This tool to measure this thing. Right. Analysis. What kind of calculations do we have? Maybe in the latter half of the table, and also what kind of graph did we make? Right. And then conclusion. What property from the graph did we use to figure out the answer to the question? What was the answer to the question? All right, so here, I'm going to pause this video while you guys are doing that write-up. All right, recordings resume. The time jump to watch this video. All right, I got the scoring rubric. I try to make this close to AP. I scored this out of 12. It's kind of a big lab, so somebody should maybe have a point. Right. I try to make it pretty close to an AP. Right. Here we go. Question: what is the rotational inertia of the pipe system about the central vertical axis? Measuring tools. Got a scale or a triple beam balance, a ruler or a meter stick, or maybe we mention both, it's okay. A stopwatch or a timer. There we go. Right. Data gathering procedure. First point for describing the setup. Set up the pipe system to rotate about its vertical axis. Tape a string to the central vertical axis of the pipe system and wind the string around the axis. Route the string around a pulley so that a lab weight can be suspended and allowed to fall vertically, causing the pipe system to rotate. Bam, that's it. That's the entire setup. So you don't have to have exactly what I wrote, but as long as you describe some kind of setup that checks the box, give yourself a point. Next point, use the scale to measure the mass of the lab weight in kilograms. Bam. Next point, use the ruler to measure the radius of the central vertical pipe. Record the radius. Bam. Next point, using the ruler and the stopwatch, measure the falling distance x and the corresponding time t. Or okay, now I said 10 revolutions, but let's not worry about it. Let's just do falling distance. Right? So falling distance and time. Maybe there should really be 2 points, but I just have one here. Think total of 12. Okay. Next point. Multiple trials. Repeat 3 trials per lab weight. Right, guys, that's always a point by AP's rubric on this experimental design. Right, you want to do multiple trials. Maybe I should have added to reduce experimental uncertainty. Right, that's always a point. Right, multiple trials to reduce experimental uncertainty. Right? And that's why I say we're going to make believe that we did trial. Next point, independent variable. Repeat each process using lab weights with 5 different masses. So we've established some kind of changes, some kind of independent variable, right? We're changing out the lab weight. Right. Right. Next, this next section I've sent to analysis. Right. We're going to do some equations. Determine the average linear acceleration. X equals 1/2 at squared. You can rearrange that and get acceleration is 2 times the falling distance divided by the falling time squared. Next point, if you have that in your procedure, that's okay. Right? Next point, determine the tension. That was elevator physics. You guys remember tension is mass times G minus A? Right? Talked about that yesterday and today. Right? Next point, determine the angular acceleration by doing linear acceleration divided by r. Right? Alpha equals A divided by r. Right? Next point, determine the torque. Torque equals r cross F. Boom. Point number 11, graph each of the 5 points, torque versus angular acceleration, right? Tau versus alpha. And the last point, 12, because tau equals I times alpha, rotational inertia is the slope of torque versus angular acceleration. Conclusion, rotational inertia equals so many kilogram meter squared. And we got something about like that right there. All right, so score yourself out of 12, toss that in the grade tray. I'll put points in the book for you. All right, you guys have a great afternoon. I'll see you guys tomorrow.